Talk to you about hypothesis testing on proportions, and we're going to consider this example problem in which a manufacturing company claims its defect rate for a specific product is no more than 3%. A quality control manager takes a random sample of 500 products and finds 10 defective items. The manager wants to determine if the actual defective rate is slightly less than the claimed 3% level. Okay, so this involves hypothesis testing because it's making an inferential claim about a population proportion of parts produced. Okay, that population proportion is very hard to assess because it's of the entire population of all parts produced. And what we're trying to do is to use a sample, a subpopulation or a sub-collection of the data, of the entire data set, to make a claim about the population proportion of the entire data set. So we use a subpopulation to make a claim about a claim and to try and validate it about the entire population. So the things that we'll be talking about, this is a topic that is called statistical inference, and the specific method or topic is hypothesis testing. Hypothesis testing uses p-values to make conclusions. Now, those conclusions are not a guarantee that we're making the correct decisions, so we have to talk about the type of errors that we could deal with, and they're called type 1 and 2 errors. Okay, so a p-value is the measure or the probability of an observed difference, and it's an evaluation of the claim of the null hypothesis that that difference occurred due to random chance. Okay, and the alternative hypothesis is that it's not due to random chance, is that there is something that's different or that is affecting it. Okay. The p-value relates to statistical inference because it helps us to decide between a null or an alternative hypothesis, i.e. it helps us to make decisions. Now, we have to know what is the cutoff level of risk that we'd be willing to endure. Oftentimes people set that level of risk to be 5%. Okay, so that is, we say if we get a p-value that's less than 5%, that's not likely to be due to random chance, and then we decide that the alternative hypothesis is true. Some people use a different threshold. Some people, for instance, use 1% and say that if the observed data has a p-value of 1% or less, then that is not likely to be due to random chance. So just keep that in mind. Okay, so when you're doing hypothesis testing, the first step is to write down your null hypothesis. That typically represents a statement of no effect, no difference, and is always a statement of equality. The alternative hypothesis, that's what we're trying to establish. Okay, and that is typically a statement of inequality. Now, unless it's specified, typically people will make will set their threshold or significance level to be 5%. Okay. In calculating your test statistic, well, you need a sample of the data, so you have to collect it. Once you collect your data, you're going to use that observed data to calculate a p-value. That's a measure of the probability of observing your data under the null hypothesis, or if the null hypothesis was true. So if you get a really low p-value like 0.02 or 2%, well, that's not very consistent with the null hypothesis then. Okay. Once you calculate your p-value, you're going to decide to reject the null if your p-value is less than that threshold of typically 5%, or whatever they set it as. Here it's represented as alpha. And if it's greater than alpha, you fail to reject the null hypothesis. For practical terms, that means that now statisticians don't use the term accept, but we go with, or if you put accept in quotes, we accept the null hypothesis. Now, it's not that the null hypothesis is true, it's just that we don't have enough evidence to decide against it. Okay. Now, if the p-value is less than our alpha, we reject the null hypothesis in favor of the alternative. Okay. Now, when we make these decisions, we can make mistakes. So a type 1 error, it's called a false positive, is to reject the null hypothesis, but the null hypothesis is actually true. Okay, so that's saying that there is a difference or an effect when in fact there isn't. A type 2 error means that we fail to reject the null hypothesis, but the null hypothesis is actually false, i.e. the alternative hypothesis is true. So this would be like saying there's no effect, but there actually is one. Okay. So in this specific lecture, we're talking about population proportions. That's the fraction of observations in a population, or excuse me, it's the fraction of individuals in a population that have a specific characteristic or trait. Okay. For example, at the start of this lecture, the trait of interest that we had was being defective. Okay. The population proportion is a theoretical value because it's very hard to actually obtain. Okay. If I asked you what is the population weight of all adult men, that would be very difficult to obtain. We'd have to actually go out and measure every single adult male. Okay. So what we'll do is we'll take a sample and we'll use data to assess things about the entire population. Now, to be able to assess it, we have to calculate a p-value, and that becomes very important to know the theoretical distribution of this population proportion. Okay. So for us, our theoretical approximation of our population proportion comes from the normal approximation. And implicitly, it's the central limit theorem. Okay, so we need to assume that we have a random sample, that the observations are independent. Then to ensure that we have an accurate calculation of probability, we need to have a large sample size so that n times p is greater than 10 and n times 1 minus p is greater than 10. Where that p0 comes from the null hypothesis. Okay, so we have a theoretical distribution of the proportion, and the sample proportion is calculated by the total number of individuals with the trait or observations x divided by the total sample size n. Okay. Now this is a random variable until the data is collected. Then it becomes a statistic. Okay. So for us, this sample statistic is 0.02, it's 10 out of 50. In this example, our null and alternative, our null is that the company claims the defective rate is 3%. The quality control manufacturer thinks it's less, thinks it could be less than 3%. Okay, so that's our statement of null and alternative. The way things currently are believed to be true is it's 3%. We want to establish or prove that it's less than 3%. Okay, so we have to understand the distribution of the sample proportion, and it becomes really, really important to know what the standard error of this estimator is, of this test statistic, before when it's as a random variable. So for us, it's not hard to prove that the sampling distribution P has variance P times 1 minus P over N. Okay, and pretty much the proof comes from the fact that the variance of a binomial distribution is n times p times 1 minus p. And so the standard deviation is the square root of that. So when we divide by n, we're going to get exactly this quantity, because the sample proportion is the number of successes in the sample divided by the total number of samples. So using the properties of variance, you can prove this in just 1 or 2 lines. Okay. So for our problem, we have this as our standard error or variance of our test statistic, our random variable. Okay. So to summarize, we have this and we have this standard deviation. Okay. We're going to use the normal distribution approximation. That's what this sample proportion is approximated by, is the normal distribution. And so when we do that, typically, okay, we're going to take the z-score. And I want to just briefly take an intermission and talk about right-tailed tests for proportions. So a right-tailed test, this pertains to the alternative hypothesis. So the alternative is that is greater than 60 in this example. So in this example, our rejection region is in the right tail. Okay. Okay. So my apologies there. Then a left-tailed test means that the alternative hypothesis is less than 10%. Okay. So that means that where we calculate our p-value is in the left tail. Okay. Then there's this last alternative hypothesis, which just says that it's different. Okay. So it's different from, it could be less than or greater than the hypothesis tailed. So that's left or right in a two-tailed test. So let's look at some pictures here. And here I calculated our test statistic, okay, for this example. So n is 500, x is 10. Our null hypothesis probability is 0.03. Our test statistic is x over n, so 0.02. Our standard error is 0.07. And we get this z statistic just by calculating the z-score using the normal distribution. Okay. Now I'm going to go ahead and show you So a right-tailed test would correspond to this area here. Okay, and we can see that the p-value of this right-tailed test is 0.002. So if our significance level was 5%, we'd reject it. Okay. Now for our left-tailed test, our rejection region is to the left here. So just keep that in mind. Okay. And by the way, I think, let me run this code. And let me run that one up there and run this one here. Okay. So my apologies. The test statistic need to be recalculated in this situation. So our left-tailed test is still to the left, but our z value now matches what's right here in our example that we started off. It's minus 1.31, and that makes more sense. So if we had a right-tailed test for this value, it'd be all this area over here. Okay, so the key point is that for the right-tailed test of an alternative hypothesis of greater, we have all the area to the right of the test statistic. For the left-tailed test, it's all the area to the left of the test statistic, and their alternative hypothesis would be less than 3%. And a two-tailed test would have two areas to calculate the p-value, greater than the value and less than the value. So greater than minus 1.31, less than 1.31 right here, and greater than 1.31 right here. And we calculate those probabilities. The right-tailed test would be 90. The left-tailed test would be 0.09, and the two-tailed test would be about 19%. So in all of these, because these are greater than 5%, we'd fail to reject that the proportion of defectives has changed, because now our p-value is greater than 0.05, greater than 5%. So it's not that unusual to observe 10 out of 500 defectives if the true population rate of defective is 3%. So 3% is a reasonable thing. Okay, here's another one, just as an example problem. So a public opinion survey is a political polling organization that wants to determine if the portion of voters who support a particular candidate has increased from 50% from the last election. So they conduct a survey of 400 randomly selected voters and find 220 of them support the candidate. So the first thing to do is write down the null and the alternative. The null is that it's still 50%. Things haven't changed. The alternative is that it's increased. It's more than 50%. So this is a right-tailed test. So we're looking at a region like this. Okay. The exact value is probably going to be to the right of the peak or the mean here. Okay. And then we're just going to input all the information. N is 400, observed successes is 220 out of the 400. Our null hypothesis probability proportion or population probability is 50%. Our significance level is 5%. Okay. So we calculate our test statistic, we calculate our standard error of our test statistic. So we have all this information. The sample proportion p hat is 0.55. Our standard error is 0.025%. Okay. From that, we calculate our z statistic. We just standardize with the information above. We get a statistic of 2. And now, remember, we have a right-tailed test. So our probability is to the right of the value of z that we calculate. and is 0.0228. So we would reject our null hypothesis and conclude that the true population proportion that supports this issue is more than 50%. Okay. So in this instance, we reject the null in favor of the alternative, and that's our decision based on the p-value and the significance level of 5%. Thank you very much.